For centuries, humanity has sought to understand reality's deepest layers, the very fabric of existence. What is everything made of? Our journey often began with atoms, those indivisible units, then their constituent protons, neutrons, and electrons, a seemingly solid foundation. But as we peered closer, these particles behaved strangely, sometimes waves, sometimes points. A duality that defied simple explanation. What if our fundamental understanding was flawed? What if particles weren't fundamental objects at all, but something far more profound? The concept of fields isn't new. James Clerk Maxwell unified electricity and magnetism through the electromagnetic field in the 19th century. Imagine a pool of water. A ripple isn't a new water particle appearing. It's an excitation, an energy disturbance in the existing water. Quantum field theory, or QFT, suggests the universe is filled not with discrete particles, but with omnipresent fields. An electron is merely an excitation, a vibration in the underlying electron field. Light, traditionally thought of as waves, is quantized into photons. In QFT, a photon is an excitation in the electromagnetic field, a ripple in the cosmic ocean of light. This isn't just theory. Experimental evidence, meticulously gathered over decades, points to this deeper reality. Take the Casimir effect. Two uncharged, parallel plates in a vacuum experience an attractive force. This force arises from quantum fluctuations, virtual particles constantly popping in and out of existence in the quantum fields. What we perceive as empty space is anything but. It's a seething, energetic sea of quantum fields, a vibrant backdrop to all existence. The standard model of particle physics, our most successful description of fundamental forces and particles, is built entirely upon quantum field theory. Every fundamental particle we know, quarks, leptons, neutrinos, each is an excitation in its own corresponding quantum field, permeating the cosmos. The forces that bind our universe are also described by fields. The strong nuclear force, for instance, is mediated by gluons, excitations of the gluon field. When two electrons interact, they are not touching. They are exchanging photons, excitations of the electromagnetic field, a continuous dynamic dance. The weak nuclear force, responsible for radioactive decay, is mediated by W and Z bosons, again excitations of their respective quantum fields. Then there is the Higgs field. Unlike other fields, it possesses a non-zero value even in its lowest energy state, permeating everything. Particles acquire mass by interacting with this field. The more they drag through the Higgs field, the more massive they become. The hunt for the Higgs boson, an excitation of the Higgs field itself, culminated in its discovery at CERN's Large Hadron Collider in 2012. A monumental achievement, providing profound validation for the quantum field theoretical framework. Mass, once conceived as an inherent property, is now understood as an interaction. A particle's inertia, its resistance to acceleration, arises from its coupling to the ubiquitous Higgs field. Our universe, then, is not a collection of billiard ball particles, but a dynamic, interwoven tapestry of quantum fields. The solidity we perceive, the very ground beneath our feet, is an illusion, a magnificent manifestation of these interacting fields. It suggests a fundamental interconnectedness. All matter, all energy, ultimately originates from the ripples and vibrations in these universal fields. This framework also provides avenues for exploring the unknown. Dark matter, for instance, could be an excitation of an entirely new, undiscovered quantum field. And dark energy, driving the accelerating expansion of the universe, perhaps the energy of another ubiquitous field, inherent to space-time itself. One force remains outside this elegant QFT picture: gravity. Einstein's general relativity describes gravity as the curvature of space-time. Reconciling general relativity with quantum field theory, quantizing gravity, remains the holy grail of theoretical physics. The hypothetical graviton, the quantum of gravity, would be an excitation of the gravitational field. Its detection, or even a consistent theory incorporating it, eludes us still. The universe, then, is a grand symphony of vibrating fields, each note a particle, each chord a fundamental interaction. From the very first moments of the universe, captured in the cosmic microwave background radiation, these fields have been at play, shaping everything. Today, at colossal accelerators like the LHC, we smash particles together, probing these fields with unprecedented precision, witnessing their excitations. This shift from discrete particles to omnipresent fields is more than a technical detail. It's a profound reimagining of reality itself. It describes a universe built on elegance and mathematical beauty, where fundamental entities are not points, but dynamic, interacting continua. Humanity's quest for fundamental truth has always pushed beyond the apparent, seeking the hidden mechanisms that truly govern. While QFT offers incredible insight into matter and forces, it doesn't answer everything. The nature of consciousness, for instance, remains an enigma. Our journey continues. New fields may yet be discovered, new interactions unveiled, pushing the boundaries of what we comprehend. The universe is not static, nor is it merely a collection of isolated bits. It is a dynamic, interwoven tapestry, a unified whole. And we too are part of this grand cosmic design. Fleeting excitations in fields that have existed since the dawn of time, and will continue long after. Beyond atoms, beyond particles, it is the quantum fields that secretly, profoundly govern our universe. A hidden reality waiting to be fully understood.